Welcome back to Computer Lessons.
A computer is a box of microscopic switches capable of simulating universes and bridging global communications through programming logic. Without these algorithmic roadmaps, the most powerful processor is just a fast electric heater, serving no functional purpose. Every digital action you witness is the execution of an algorithm, representing a finite set of unambiguous instructions designed to solve operational problems. Software programming translates our human intent into exact, mathematical sequences that dumb silicon can execute without hesitation. Before writing actual code, software engineers use flowcharts to visually map the logical path of raw data through a complex system using geometric symbols. This visual mapping allows developers to identify infinite loops before they become expensive logical errors within a live server environment. The fundamental concept in programming logic is the variable, functioning as a labeled digital container for storing temporary information directly in active system memory. Whether tracking a high score or physical coordinates, programmatic logic dictates exactly how these specific variables interact and continuously evolve. Decision-making in code is handled securely through conditional statements like the if-else construct, relying entirely on strict Boolean logic to evaluate specific mathematical conditions. The machine evaluates this condition as true or false, dictating whether emergency cooling fans activate instantly or gracefully remain dormant. Complex computational tasks demand the massive repetition of instructions, a process handled elegantly by programmatic loops like the powerful for and while iterative constructs. Instead of manually typing commands 10,000 times, a designated loop automatically repeats crucial actions until a specific mathematical condition is met. Algorithmic efficiency is measured through a mathematical concept known as Big O notation, explicitly describing how an algorithm performs as operational data exponentially grows. A poorly designed algorithm might work perfectly for 10 items but will crash enterprise server systems when forced to handle millions. Sorting remains a classic algorithmic challenge where we take a chaotic list of raw digital data and systematically arrange it into perfect sequential order. Simple methods like bubble sort are easy to understand visually but perform incredibly slowly when tasked with organizing massive relational databases. Searching constitutes another foundational pillar of programming logic, with the binary search algorithm acting as an absolute masterpiece of computational efficiency and mathematical elegance. By splitting a sorted dataset perfectly in half, a binary search reliably finds one specific item among billions in just 30 steps. Recursion is an advanced logical concept where a software function calls itself repeatedly to efficiently solve increasingly smaller versions of the exact same computational problem. While mind-bending to visualize conceptually, recursion provides elegant software solutions for navigating complex file directories, provided you establish a clear stopping condition. Data structures dictate the physical ways we organize raw information in active memory, so that our custom algorithms can access everything with maximum efficiency. Models like arrays, linked lists, and stacks feature unique computational strengths, requiring engineers to select the perfect structure to prevent processing delays. Hash maps represent perhaps the most powerful data structure available, effortlessly allowing for nearly instant information retrieval by utilizing a complex mathematical hashing function. By converting a unique key into a physical memory address, this constant-time complexity forms the unbreakable foundation of high-performance modern web applications. Modern programming embraces object-oriented logic, structurally grouping related data and active behavior into self-contained modular digital units called objects. Instead of writing disorganized sequential instructions, creating a unified object featuring distinct properties makes complex software architecture easier for large human teams to maintain reliably over extended life cycles. Abstraction serves as the critical engineering process of hiding complex internal system details behind a much simpler programming interface. You never need to understand the underlying electrical engineering of a graphics card to simply command the operating system to instantly draw a smooth red circle. Functional programming offers an alternative logical paradigm, treating computation purely as the rigorous evaluation of mathematical functions while strictly avoiding changing internal states. This disciplined approach drastically reduces unpredictable runtime bugs by mathematically ensuring identical data inputs always produce the exact same predictable digital outputs safely. Concurrency and parallelism represent advanced logical techniques, explicitly allowing a single program to seamlessly execute multiple demanding processing tasks simultaneously. While splitting heavy tasks into separate simultaneous threads is absolutely essential for modern multi-core processors, this dramatically introduces dangerous computational race conditions over shared volatile system memory. Debugging remains the methodical, logical process of finding and removing critical software errors, a historical term coined when a moth jammed an early computer. It requires an analytical detective's mindset, patiently tracking the invisible flow of volatile variables through the massively complex algorithmic code-based tree manually. Pseudocode acts as a conceptual bridge directly between natural human language and raw machine code, allowing experienced developers to safely sketch out architectural logic. It focuses purely on the theoretical problem-solving process itself, rather than worrying about specific required semicolons, ensuring the foundational logic remains structurally sound. The transition from a conceptual logical flowchart directly into a functioning high-level language like Python is handled flawlessly by highly optimized dedicated compilers. These vital software tools systematically translate our human-readable logic directly into the raw binary machine code that the central processing unit natively understands and safely executes. Regular expressions, universally known as regex, provide a powerful logical syntax for rapidly searching and flawlessly manipulating massive text strings based on complex algorithmic patterns. A single line of regex automatically validates email addresses, systematically extracts hidden phone numbers, or completely scrubs sensitive corporate financial data efficiently. Boolean algebra remains the absolute unyielding mathematical foundation of all programming logic, utilizing essential core operators like AND, OR, and NOT perfectly to evaluate binary states. These fundamental logical gates are physically etched into the microscopic silicon architecture of the processor, miraculously turning abstract mathematical computing theory into physical reality. Error handling represents the necessary logical foresight of an experienced programmer to correctly anticipate exactly what might catastrophically go wrong during live software execution continuously. A robust enterprise program uses specific conditional fallback blocks to safely intercept critical fatal errors and consistently fail gracefully instead of crashing the operating system. Application programming interfaces, widely known as APIs, are strict logical software contracts allowing completely different proprietary software programs to seamlessly communicate securely across the internet. They clearly define exactly what specific network requests are authorized and exactly what rigidly structured digital data payloads will be automatically returned to the application. Version control systems intelligently provide a truly flawless logical timeline of a software project's entire collaborative history, safely allowing distributed global developers to branch and merge code safely. It mathematically ensures that multiple professional engineers can simultaneously work on the exact same complex codebase without ever accidentally overwriting each other's critical progress. Cloud-native logic involves explicitly designing complex software architectures to run seamlessly in massively distributed environments scattered across multiple global data centers simultaneously. This modern approach requires successfully breaking a monolithic application completely down into extremely tiny, highly independent, rapidly communicating digital units universally known, fundamentally as infinitely scalable microservices. Artificial intelligence represents the next major paradigm evolution of software logic, where we finally stop giving rigid rules to computers and instead organically find deep hidden data patterns. However, at its fundamental mathematical core, even the most advanced artificial neural network relies remarkably heavily on raw linear algebra and massive algorithmic weightings. While we use these highly sophisticated logical constructs to build complex applications today, everything undeniably rests entirely on the computer's fundamental ability to accurately count. In our next instructional video, we will dive directly into binary math and comprehensively examine exactly how processors utilize basic ones and zeros computationally globally. Logic undeniably remains the ultimate universal digital language, seamlessly connecting your creative human brain directly to the raw physical hardware of the central machine.
Considering everything we heavily covered today, which foundational programming concept actually intimidates you more right now? Understanding complex algorithmic recursion or perfectly mastering memory-efficient data structures comprehensively? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.